My name is Micah Whitaker. I'm a software architect on the big data team here at Cerner. And one of the things I want to make sure to clarify before starting this talk is that I'm not really going to go through insights we've found in data, but more about a new set of tools that we can start using to find that insight. Because one of the things that we at Cerner are doing right now is building a lot of great applications on the data, transforming it into help build those apps. But one of the nice things, or one of the qualities about big data when you move to that second level, is now that you have all this data at your fingertips as a resource, what can we start learning from this data to build more knowledge as opposed to it just being raw data? And so on the normal, if we were looked at the normal set of tools that we have right now, the common one that everyone uses is Hadoop, MapReduce processing. Let's talk about this morning at the keynote. But we have that batch-oriented system to try and start getting knowledge out of that data. We can then maybe look at other ways to interact with the data, something like Hive queries, which everyone kind of knows under the covers equates to MapReduce jobs as well. Maybe we want to write scripting instead of MapReduce. Or maybe some of the knowledge that we want to try and derive actually doesn't work well in the normal MapReduce framework. Actually, it works better in graph processing. So there's other infrastructure and projects out there that we have at our disposal with Apache Giraffe. And then if you're kind of, that next level, you're an awesome machine learning expert, or just maybe dabbling, you might play with some of the machine learning libraries that are out there like Mahout. And all of these kind of sit on top of MapReduce. And, it's the shortcomings and the benefits of that MapReduce processing are what you inherit, essentially. And there's been a few other cases where people have tried to build other processing systems or other ways to interact with the data. Things like Cloudera's Impala, which is a faster SQL-like querying system on top of HDFS file systems to kind of give you that business intelligence, interactive things that you might be used to with other products like Vertica. Or sometimes your interaction with the data, it's not really at rest. You're not querying it. It's more flowing through your system. So maybe you're using something like Apache Storm to try and interact and kind of derive information out of that data flowing through your system for maybe a variety of reasons. Maybe you're building certain solutions, but at the same time, another team wants to look at it and kind of come up with a new concept. And if you look at these different solutions, there tends to be a couple complaints that people have. The first ones when people talk about trying to use MapReduce is, it has slow startup times because it has to spin up the mapper jobs and the reduce jobs, and that JVM time's a little slow depending upon what you might need to be doing in your initialization. Or the I/O is very expensive as I'm reading the data into one JVM to process it, to write it out, to then pick it up by the next, and so on. So a lot of times people will complain about that. It's also very much batch-oriented, meaning it really is set up to let you do DAG-like processing of taking data in, processing, write it out, taking large volumes of data through the system, as opposed to small discrete systems. Storm is better for those discrete systems, or discrete data going through, but MapReduce as a whole is better for that batch. And then that batch concept actually kind of makes it a very difficult barrier to entry for some of these more iterative algorithms. So I want to process this again and again, or continue to train models on it. And so systems have to do something a little wonky or weird when they're doing the processing. Like Giraffe as an example, wants to keep processing again and again, so it has written some custom code to get that to work. And the last is if you want to move outside of the MapReduce framework, that's where you start getting into things like Impala or Storm. You kind of have to write these custom execution engines, and some of them might be custom code to run inside of those engines. And so it's kind of an investment cost to be able to move or shift or try to accomplish some of these tasks outside of that MapReduce. And kind of one of the ones that's not up here is just in general the barrier to entry. We have a lot of smart, awesome engineers writing MapReduce jobs, processing that data, building it up in the right form for our applications to work and succeed. We also have a lot of smart data scientists, math whizzes who want to start playing and experimenting with that, but maybe don't want to learn the ins and outs of Maven and Java and packaging and assembly and shipping out to a cluster. They want to be able to play with the data and experiment with it in a fashion that's useful for the tools they have accessible or that they're used to using. Scikit-learn is an example if you were at Chris Finn's talk yesterday. So with all these kind of shortcomings, a couple of years ago at the University of Berkeley, specifically the AMP Labs, they came about a project called Apache Spark. It's recently gone through some maturation. It's now part of the Apache Foundation. It actually had its 1.0 release last Friday, which is awesome if you have a presentation based off an old version and they give you a new one that have to rewrite things on in the last minute. But one of the things about it is, there's a lot of kind of marketing terms about what Apache Spark can give you, but we're kind of going to drive down into what it actually is and what kind of possibilities it's going to provide, also how it'll kind of incorporate into our ecosystem to solve different problems. So if we first kind of start trolling through the marketing speak on Apache Spark, the first thing you're going to see is that it's in memory. It's trying to achieve a speed boost by keeping more data in memory, keeping the processing in memory, as opposed to kind of the system with MapReduce where you read data in, write data out, read data in, write data out, and you have that constant disk I/O. Additionally, they talk about its capabilities and functionalities. It supports SQL, like queries on top of the data out of the box. It handles the streaming capabilities of incremental data flowing through and trying to process it that way. And then it also comes, it tries to satisfy those complex analytics of machine learning or graph processing that, Hadoop or MapReduce when it was first written, wasn't really focusing on that. It was trying to focus on, large volume batch processing. And kind of the most well thing it's known for is that it's claimed to be 100 times faster than MapReduce. I'm pausing because I'm kind of expecting all the people who write MapReduce jobs to kind of go, ooh, ah. So the subtext to this is actually that it says it's 100 times faster than MapReduce when it's in memory. If you have to write everything out to disk, it actually also claims that it's 10 times faster than MapReduce. And so thinking about that as performance-wise, if you're reading and understanding how Spark works, the bare minimum of its performance is kind of the current state of MapReduce. And that's a nice thing or a nice feature to make us look or start experimenting with this type of project. But as I mentioned, this is kind of the marketing speak. It doesn't help you as an engineer understand how this system is going to work, how your code is going to execute, how you can do anything really useful with it. All it does is help a manager or an exec maybe say, yeah, let's go do that. So the next kind of definition of it is a fast and general execution or fast and general engine for large-scale data processing. So it's set up to try to handle processing both in a batch-oriented and streaming fashion. And then the other, it's still very vague. What is this thing? The other definition it provides is it's basically a DAG execution engine that supports cyclical data flows in memory. And if you're like me, you read this and said, something doesn't seem right with the words in this definition. And so let's expand what that acronym was, a DAG, a directed acyclic graph. And you're still reading this and you're going, something's not right. It's kind of a WAT moment, but it's not, you aren't right there. And then eventually you kind of piece it together, is that there's two contradictory words in this. Acyclic graph and cyclical data flows. How does that work? And we'll kind of break that down to actually see, how Spark does its processing, but then also how does it help those cyclical data flows or iterative processing needs that you might need for that higher level computing problem. So the base, if taking a step into the internals or the base concepts of Spark, everything starts with what's called an RDD, or a resilient distributed data set. This is the data that you're going to be processing on. It's spread throughout the cluster. It's available, to be parallelized for you to get that nice batch processing or that nice distributed computing. And as far as the concepts or the key things they're trying to build inside of an RDD, they actually steal most everything from what you would get from a Hadoop HDFS file system and MapReduce processing. So we want the locality-aware scheduling. We want to move the compute to the data as opposed to the data to the compute. We need scalability, so we need to be able to break this data out across the entire cluster for us to process it. We, of course, need to handle fault tolerance, because as you, at the keynote this morning, talked about, we need to be able to take a node just dropping out or a cloud forming and frying everything in a cluster. We need to be able to handle that and keep processing and be resilient to that. And kind of the one difference that it has over a normal MapReduce, where MapReduce normally has, I have my input data and I have my output data, but any data I'm producing in the middle is just for me and will go away at the end of it. Spark actually tries to let us use that intermediate data or those intermediate working sets to then build and branch off of to build new data. So we want to, some of this might not be that earth-shattering if you are using a normal DAG building system like maybe Apache Crunch, where you can use P collections and fork and various points, but in a normal MapReduce, this is something that isn't commonly there. So it wants to be able to let you do parallel operations on those various working sets. And so if we look at these, one of the key things that kind of sticks out besides the last capability is how does a system that is holding all of our data in memory going to be fault tolerant? Because with normal MapReduce, if a compute fails, we just spin up that JVM and we try to compute it again. We get the 4 tries or however many configurable tries until we start saying, nope, this data is so bad I can't even keep going. But if the data only exists in memory, how are we going to be able to handle that failure? And so when reading through Spark and its motivation and how it tried to actually implement an RDD, it kind of came up with 2 different options. The one on the one of them is the distributed shared memory. So this would be a lot of ad hoc reads and writes to random values inside of this data set. And of course, if you want to be resilient to that, you're going to have to checkpoint it regularly to another system, because otherwise, if it falls out of memory on a machine or that machine dies, you're kind of hosed. So it kind of is distributed shared memory with checkpointing to kind of handle fault tolerance. Or there's the option of logging the updates. So how does this data get updated and processed? What's the history of it? And so let's kind of take it through an example of how each of these would maybe try to be resilient to failure. And it kind of helps guide us to why they pick their final solution. So you as a developer, we're building a system. It's the best system in the world. It sets you on the path to be able to build new things based off of it. So a small, tiny castle that's beginning to, your Lord of the Rings set that you're going to build the entire Middle Earth with. But you need to be worrying about protecting this, right? Because faults happen. More specifically, things you don't want to play with your toys will come along and steal pieces, smash it, who knows what. So how are you going to be able to handle, recovering from your little castle that you had all these high hopes and dreams from being destroyed? So with the distributed shared memory, we essentially have built the castle, it's sitting in our memory, and now, to be able to be resilient to that failure, we have to start making copies of it and distributing across the cluster. So first we start by checkpointing it, writing out to our disk. That way, maybe if this process just got restarted, we can at least recover from there. But then we also maybe have to worry about replicating it to another node, because if that node goes away, we need to be able to recover from that. And we start seeing that, while we started with one simple castle, we now have 3 copies of it. We had to buy 3 different Lego sets just to be resilient to that evil little kid. And it kind of starts to be expensive, both CPU, processing-wise on the machine, network-wise, sending all the data across the cluster, and it's not as efficient as it possibly could be. Additionally, you're only as resilient as the last checkpoint, and if you're doing the ad hoc updates, you might be out of date the moment you actually start the checkpoint. The other option was the logging of the updates. So how are you going to recover that castle? And the answer is, just keep all the pieces in the instruction manuals and rebuild the system whenever you need it. And if you think about the 2 different models, one might seem slower because you have to rebuild the whole castle from scratch, but one is also a lot simpler and a lot easier to do. And if Spark lives up to its promise, it should be able to recompute that castle just as fast as you bringing back a node. And in most of its testing and benchmarks that it's published, it actually is able to. So essentially, we take the options, we eliminate the distributed shared memory, because that's really complicated, really costly, and we stick with logging updates. Now, it should qualify this. We're not logging updates to discrete values. We're actually logging coarse-grained updates. The analogy actually works very well with the Lego instruction manual. Like, you don't see where every single piece goes. You see, as the steps to build up to that final thing. So that's what it does, is it keeps track of where did you start and where are you going to end, and we'll keep track of all the steps in the middle across the entire data set. So this brings up a few capabilities or a few restrictions depending on how you want to look at it. The data sets are immutable or read-only, meaning you can't suddenly rewrite a single value inside of it. You'd have to create a new copy of the data to do that. It's partitioned because obviously we have to be scalable, so the data is spread across the entire cluster. But this model doesn't work well for ad hoc async updates to that shared state. You have to take the data through the transformations to actually get to the various places you want to go. So, if we were to continue the Lego analogy as far as building up this castle, we need to be able to if we want to be able to recover from any faults, we need to kind of start with a stable RDD. And there's two options, or a couple options, for what you can actually start with. Excuse the horrible misspelling of parallelized. You can be a parallelized collection, so anything you're holding in memory, you can distribute it out to the cluster. Or you can start with something like raw files on the file system, HDFS, JDBC, and there's ways to build in another system. But essentially, this is your base layer. If this thing is not stable, you're not going to be able to be resilient to fault tolerance. And a lot of them, like HDFS, it's not a big worry. You just go back, read the data up, and keep going. But if you were to choose a different one, just keep in mind you might be on shifting sands. So now let's start looking at a little bit of code. Quick sidebar on this. All the code examples I'm going to show are in Scala. Spark out of the box supports Python, Java, and Scala. I'm not a Python person, so that's why I picked the JVM language. And then I also landed on Scala because all the Java examples, because of Java's lack of support of closures, made all the code examples fill up the page. But like, keep this in mind. This is already kind of a quick win, just looking at the code, because you have all of those data scientists who love Python, now get to start playing with the data in the exact same way that the batch-oriented or processing developers are. And they can pull in whatever libraries they're used to of scikit-learn and et cetera to start processing the data. So now actually, what is this code doing? To start with Spark, you need to start with what's called a Spark context. Spark has kind of this hierarchy or this relationship of all of your data is processed inside of a Spark application. The Spark context is responsible for creating the application, so there's a one-to-one relationship with that. And the Spark context will exist in something called the driver program, and I'll talk about that later. But in this case, all we're doing is we took in the configuration for the master, so where's the cluster we're starting talking to. We gave it a very creative name called Spark app, and we gave it the configuration properties for things like, which ports or settings we want to maybe use by default. But using this context, we also can do a few other things. We can use things like accumulators, which are kind of an incremental counting value that gets distributed and shared across the entire cluster. We can use broadcast values, which are we take one value and we send it out to all the different nodes in the cluster, and it's now read-only. So it's not really like there's any shared state option of like a cluster or a node can write something back to you. All it can really do is increment a counter. And kind of the core thing, or the reason I brought it up here inside of talking about RDDs, is it's the main entry point to create that first RDD, or that stable RDD in which we build. So as far as a parallelized collection, we use Scala, we take a collection in memory and we say parallelize this, and it ships it out. Obviously you would never do this with this small of a memory, or this small of a collection, because you might as well just be doing it on one JVM. But if this was 1 million values or et cetera inside of a map, you could shift it out. And it would break that thing up and partition it for you across the cluster as you need it. More interestingly enough, you could read in values from HDFS, you can read in raw text files. So in this case, we're taking in a path that actually points to a folder full of text files, reading that in, and we get this raw RDD to start processing with. The nice thing is, and the reason this is succinct, is essentially we have a raw RDD of strings. With Scala, it infers all the types for us, so we don't have to declare that explicitly. On RDDs, you basically have two options of what you can do. You can do transformations, and you can do actions. And there's a couple examples, a breakdown of what you can do in each one. Obviously, transformations means I'm taking all the values in the raw RDD, I'm going to apply a map to it, I'm going to get a resulting RDD that now has, is the output of whatever that function was, or I flat map, or I filter out values I don't care about. Actions, on the other hand, are more of like go forth and do something situations. So you have this RDD, take all of the data, bring it to one machine and let me collect it, or take the first 10 out of the values, or count them for that matter. Simple things like that. And there is this distinct difference, though, in how they actually execute. transformations are lazily executed versus actions say, actually go do something and send the data back to the driver program. So transformations basically are nodes along your DAG, and the actions are the actual endpoints in which you would end at. So let's work through the Lego example. And we start with a stable RDD, that raw RDD we read out of text files, and we want to apply a map function to it. So we take that raw RDD, map it. It's all string values, so we send it through a parse method that makes sense, and we get back out of it a model RDD. And then, after that, let's apply another transformation, in this case filtering. We'll want to filter out anything that in that model that had a cost less than 0. We don't want to care about free stuff. Let's only care about the things that cost money. And we now end up with a filtered RDD. And then finally, we're going to count all the values. So one interesting thing is, and it's subtle, and I'm not a graphics designer, so I'm trying to imply it, but you'll notice that these aren't actually stacked on top of each other, because nothing's actually happened. I built the model RDD, I have it inside of my program. I built the filter RDD, I have it inside of my program, but I've not read data out of an HDFS file system. I've not read it into memory anywhere. I've not distributed anything out to the cluster. It's actually when the action happens that it would actually do something. So essentially, I call filter.count. When my program actually executes, it snaps all the pieces together, and I've built something. I still can go back and access all those intermediate RDDs if I want, but it's not persisting them, it's not keeping them around unless I need to, and it's not doing them unless I need to. Now, if we actually look at how Spark behaves by default, interesting enough, if I do a count, what actually happens is Spark doesn't keep anything in memory, and I essentially run this DAG 3 times in a row. This could be good or bad depending upon what your use cases are, but it's just something to keep in mind. Since everything's lazily executed, it also is lazy as far as what data it actually stores for you or keeps around for you as far as processing efficiency. So you as a developer or as a designer can start being smarter about, hey, I'm going to actually use that filtered RDD again and again and again. Let's stop that computation. Let me instead persist it. And persist it doesn't mean I'm going to write it out to a file system. Persist it means I'm going to keep this thing in memory to be able to reuse it again and again. And then one of the things, though, is once this stuff now starts existing in memory, you have to be resilient to failures. So if a node goes down, it normally is only holding a portion of your RDD. And so that portion or partition is actually going to get recomputed on the fly based off of that DAG that you've described. So those 3 Lego blocks knows how to create that guy back. There's also another method if you want to use it called cache. This one is just a simplification that says use whatever the default storage level is. So I've used the term storage level. What does that actually mean? Spark lets you, based off of how the data exists or how what characteristics you know about the data, you can choose a variety of different storage levels. By default, it's going to keep all the data in memory using simple JVM serialization. If that is not the most compressed or most efficient way to maybe store something in memory, or you're going to blow the heap on all of your data, you can choose to use the model-only SIR and write a serialization, like a cryo-based serialization, to compact it down to fit in memory better. If you know that it's even then not going to fit in memory, you can choose to actually have it hold as much as possible in memory and spill the rest out to disk. Or, going with the lowest performing, you can say disk only, meaning don't keep this in memory, but store it out in a temporary location for me to pull this up as needed. And kind of the last set of options you have as far as storage levels, in this case it's memory only 2, which means I'm going to keep this in memory, but actually replicate it across the nodes. This is not the suggested way to do it for fault tolerance, although it seems that way. I can have quick recovery, it's replicated. The suggestion for this would be only if you have a long-running or a web app that is doing ad hoc queries and you don't want to be impacted by a downtime of recomputing the partition. If you're just doing normal batch processing, let Spark recompute that partition without having to worry about the cost of replication. And to keep in mind, this says 2, but you can say 3, 4, 5, however much you want to waste on your cluster as far as resiliency. One thing to keep in mind is that the RDD lifecycle is contained to the Spark context or that Spark application. So I know there's a lot of teams here that kind of interact quite a bit, and if you have everything loaded up into memory, a lot of teams could start doing processing based off of that. That's actually a great case for trying to work on integrating. It obviously brings in a lot of problems as far as dependencies and assembly and how to get everything in one place. So it's kind of a challenge to go through if you want to kind of take advantage of building the RDDs once and sharing them across teams. But if you can't do that integration, you can also actually persist these guys out. And you can persist them out as text files and sequence files. There's a specific variation of an RDD called the Java pair RDD, which can write out to any Hadoop format, or input, or excuse me, any Hadoop output format. And then specifically, there's one action called a for each that you can apply to an RDD that Spark kind of reserves for side effects. So I'm going to apply this function, and when I'm applying this function, it's going to write out to an external system. Obviously, you're going to have to worry about scalability and denial of service attacks, but it's there if you need. And so we've kind of now talked about that DAG part. We've built the RDDs. We know how the DAG works and how it flows. So how does the cyclical data work? Essentially, this is the structure of what the program actually looks like executing on the cluster. You have a driver program that has your Spark context. It tells the cluster how to build the RDDs. It talks through the cluster manager to acquire resources. I need this much memory. I need this many cores. Spin up these JVMs, perform the processing, etc. And the cluster manager might vary depending upon your deployment. But that driver program basically can be the one that reissues, run this again, or recurse down this function until the data set fits what I need. As far as the cluster manager, it by default will, or Spark out of the box runs on all of these various systems. So Hadoop Yarn, Apache Mesos, Spark has a standalone cluster if you want, and it runs on EC2 and has a script that actually is pretty cool. Given your credentials, you tell it to spin up a certain size cluster, it spins up the cluster. It actually spins up for you a CDH4 Hadoop cluster sitting right next to the Spark. And the reason I actually call this one out is it's an interesting concept of, instead of MapReduce where the processing is actually sitting on the same machines as the data, since Spark inherently has a different data locality pattern than Hadoop, some of the performance testing has actually said pulling the data once across the network out of Hadoop into Spark and letting Spark worry about data locality and memory is just as performant as dealing with, sitting the Spark cluster directly on top of HDFS. It's kind of an interesting concept. It's something we're definitely going to have to work through and play around with to see how well it works. Multi-tenancy is actually a topic that I think we could probably go into a whole nother session on. Basically, you as a Spark application get to choose how much memory and CPU you want. If you don't specify any, you try to claim as much as you want, which means on a cluster, you could have some problems where someone didn't restrict themselves, and then the FIFO system kicks in, and you're now subject to wait until they start giving things back. Spark applications are actually multi-threaded and have their own set of scheduling resources, so they by default could be FIFO, they by default could be fair if you wanted, and then depending upon what system and cluster, you could have static or dynamic resources. So at this point I need to scale out and claim more machines, or I need to restrict myself back and no longer take up as much memory or CPU. So multi-tenancy is a big problem, or something that's definitely going to have to be proven out before we can probably adopt it. So that's kind of the core of Spark, is that building of the RDDs, that batch processing. But there's a lot of other projects and a lot of other things to help people wanting to play with the data outside of that batch processing. We're still kind of essentially at this point just duplicating or eliminating or duplicating functionality of MapReduce. So looking at the Hadoop ecosystem, if you're wanting to kind of ease your way in, a lot of people here at Cerner are building Apache Crunch pipelines. So what you can actually do is convert your pipeline from MapReduce to Spark with this amount of code. There's a little bit of POM fiddling, obviously, to swap out Crunch, to swap in Crunch Spark as opposed to Crunch Core, or in addition to Crunch Core, and a few other dependencies. But essentially, you change your pipeline implementation, and of course, a little bit of the connection properties, and go. You now actually have a Spark application running. Obviously, that driver program only is going to support DAGs. It's not going to do the cycles, but it's at least gets you there, and you can start playing around with the pipeline. Interesting enough, one of the problems that at various points of the last couple of years my team has worked on is trying to bridge the gap between I've written this code that runs inside of Storm or I've written this code that runs inside of MapReduce. Is there a way for me to actually reuse that same code in both places? And Spark Streaming tries to solve that problem and gets fairly close, a few little API tweaks here and there, and a few more concepts that exist inside of streaming that don't exist inside of the normal Spark. But essentially, it tries to break down that problem to give you that near real-time processing. So can I process the data faster than trying to process all of them at once, but I can process them in incremental things. So if we start back with the example, I've got a big pile of Legos. I add in Spark, I get a castle. With Spark Streaming, we essentially no longer have that giant pile of Legos to start building on initially. The Legos are going to come in incrementally. So Spark actually starts dividing them up into smaller piles. We send it through Spark, we get a smaller castle out. And we keep doing this at regular time intervals. And so what this is basically saying is we switch from saying build me an RDD to give me a discretized stream or a D stream. And that stream will basically break things up to say, here's the RDD at time 0, which is all the values that came in inside of that time period. Here's the RDD at time 2, time 3, etc. And all of the same RDD operations are available to you. Interesting enough, you can actually mix the two. If you have a RDD that you built out of HDFS and you want to merge or join these operations with data that's flowing in, you could do that. The same join operations, these are essentially RDDs. Additionally, if you want to instead have a sliding scale of data, so I don't just want the data at that time period, I need to look that, okay, maybe I've got updates in the past or maybe updates in the future that I need to be aware of, so I can set up a time window to overlap multiple. And so what this actually does is that window at time 1 basically is a larger RDD for you to operate on. And you'll kind of notice that at this point, all of the processing is at the RDD level, and all the guarantees of processing is at that level as well. As far as code changes, you switch out the Spark context to use streaming, and in this case, I say a period of 1 second. So that means it's going to start looking for data, group them into 1-second buckets, send them through my processing, and output them. In this case, I'm creating that stream using the previous context, using a socket stream. I then start applying functions to it. I say start, and I say run until I'm done, or await termination. And so that basically, I've now created a long-running process that'll break up the data as it's coming in into the small discrete values of 1 second. There's a few sources out there. Obviously, there's Socket if you want. There's also Kafka, Flume, Twitter, ZeroMQ, MQTT if you're into the Internet of Things type protocol. But one of the things to keep in mind is that your recovery and fault tolerance is actually shifted a little bit now that we're talking about streams as opposed to normal Spark, and that your recovery is still based off of the source that you're choosing to have for this information. And so talking about fault tolerance, you get essentially guarantees of exactly once processing and at least once persistence. And so what this actually means is exactly once processing means we're going to reprocess this and recreate it the exact same way no matter how many times we fail. So it's not really I'm only going to process it once, but I'm going to make sure it always looks the same no matter what. But that ability to recover means that you could be persisting multiple times if you have something that causes side effects or actually writes out. So let's take it through a failure scenario. So I'm reading data out of a source. The data flows to a specific slave. By default, Spark actually replicates the data over to a different slave just to give you the ability to recover. And then that first slave will actually try to build what you're trying to accomplish. If something out of your control starts playing with your Legos and nodes fall apart, how a cat can sleep on Legos, I don't know. That first node is dead. That second node has the copy and can keep building for you. Now, there is a potential for data loss, in all honesty. So in this case, the first slave's acquired the data, but it actually dies before it ever replicates it. That second slave has to go back to the source to get the data to process it and hope to recover. If that source isn't resilient or doesn't keep the data around more than one read, you've essentially lost whatever data that could possibly be there. So just keep that in mind when you're choosing the sources and trying to build this system. So that's kind of the replacement or the stream thing. Now let's kind of talk about that SQL capabilities, or to be able to do that ad hoc analytics or poke around the data in a certain way. So as Hadoop people, we love Hive. It lets us do that quickly. If we mixed Hive plus Spark, we get Shark. And you kind of can interact with Shark in two different ways. One is you can continue to use Hive exactly as you have it, but swap out the engine underneath of it. So instead of it kicking off MapReduce jobs, it kicks off Spark applications and Spark jobs. So the goal here is that actually same level of interaction, you just get the performance boost of Spark. You additionally can start creating RDDs based off of Hive queries. So as a data scientist, if you went to a team and said, I want to play with your data, how can I do that? And the team said, here's the Hive tables. Just start querying them with SQL to build them in and get your models. You use hcatalog and the Hive metastore so it reads in them correctly. It's a nice lower barrier to entry for them. And they're just often running with SQL, transforming the data how it makes sense. Interesting enough, with the 1.0 release, they've actually come out with Spark SQL. It's not completely replacing Hive. In fact, actually what it's doing, or Shark, what it's doing is it has a new execution engine. They kind of want to rip out the guts of how it sits on below Hive and operates. And it has a little bit of limited count situations, but essentially you can write SQL on top of RDDs, on top of Parquet files, or on top of existing Hive tables. So, we read values in from a text file, we create a table, and we run this SQL statement, say, give me all of the teenagers in this population. So it automatically is now filtering, mapping and filtering as appropriate, and you're just writing SQL at that point. It also has a nice advanced feature of DSLs, so you kind of write it out like this and it automatically filters for you. As far as that higher level graph processing, Spark comes with GraphX and Bagel, kind of as replacements or competitors to Google's Pregel. Well, it's not really a competitor, that was never open source, but kind of as an implementation to let you move out of that data parallel processing and more into the graph level processing where appropriate. Bagel is actually now deprecated with GraphX now being released, so there's a replacement there. So if you're going to start up and running, skip Bagel. Now for the people who like machine learning, there's actually projects built in to Spark, which is called mlib. And keep in mind, this is available both in Python and Scala and Java. And actually, interesting enough, the Python implementation is built directly on top of scikit-learn. But all of these common machine learning functionalities of linear regression, clustering, collaborative filtering, et cetera, you can kind of get out of the box. And apply them directly to the RDDs that you might have built through Hive queries, through reading in data, et cetera. So one of the things, though, we've kind of been talking about is we're still kind of stuck in this development life cycle of save, compile, package, ship, execute, find out it didn't work, repeat, go back through it again, which isn't the best environment. So by a quick show of hands, who loves a REPL? Okay. Spark actually comes with what's called Spark Shell, and it has this for both Scala and Python. And in Python, it has it also as IPython, if you were used to that type of environment. But it's kind of a nice way for you to start experimenting first. So I talked about lowering the barrier entry of, let me spin up a Spark Shell, read data out of someone's Hive table, and I can now start applying machine learning algorithms directly in a shell, again and again, as much as needed, tweaking and setting. And essentially, no longer do I have to package and ship the code. I can just do all of my experimentation there. Now, obviously, that's maybe not the production way you want to run your models or run your system, but it's great for actually writing the system up. So kind of to close on a few lessons when thinking about starting to tackle Apache Spark. The first one is to know your data. By default, Spark will partition the data out, but every method or every filter will actually let you override or continue to partition it out. So knowing how your data will work best and parallelize best is something that's key and important. The second lesson is know your data. Certain computations will hold more values in memory, will try to bring more into memory, and if your stuff won't fit, you're going to have a bad time. Third lesson, know your data. The storage levels, knowing how your data is going to be represented inside of memory will help you choose the right storage levels, might actually influence how you construct your objects. You can look through their tuning guide and how to improve things, and they'll tell you to use things over Java primitives over things like complex objects. So you might try to pick or change your approach based off of how things fit. The last lesson, know your computations. So Spark will try to, as I said, Spark is kind of lazy execution. You need to be able to be smart enough to know when to let Spark recompute on the fly versus when you need to be smart enough to tell Spark not to recompute because it's a very expensive operation. So in closing, this tweet kind of essentially sums it up. Spark is awesome, but it's not easy, and it's not going to be something we can roll out anytime or immediately or tomorrow. It's something that as developers, you're going to have to learn how your data and how your system's going to work. As ops people, we're going to have to know how to run a cluster. But as far as getting started, I have an example project out there that will let you play with about 11,000 different Lego sets worth of data. Has a few example Spark applications, instructions on how to get a cluster up and running, and, how to run the different example projects. And additionally, there's a bunch of nice links out there for you as a developer to play with. Interesting enough, they have Spark Summit and have the YouTube channel full of videos. So who cares about Game of Thrones? Go watch Spark videos on YouTube. And then kind of as a caveat, Spark is good, but it's not awesome. And that last blog post is a good rundown of kind of someone's trials and tribulations trying to get something even running after several months of trying to do Spark. So it's going to be a journey. It's not going to be immediate. And with that, I'm actually out of time. But if you have any questions, feel free to grab me later or at, back at campus. So thanks.